Good morning, everyone. I'm Yuling from Chinese Academy of Sciences. It's my great pleasure to attend this meeting. Today, I would like to present my paper related to almost universal hash functions, definitions, constructions, and applications. My presentation will cover the following aspects: the background introduction, and then our new definitions of RKA-AXU function and RKA-AXU functions, and their constructions named RH1, RH2, and RH3. And finally, I will show you the applications in the design of related key secure maps and TBCs. Firstly, it's about introduction of universal hash functions. Here is one of the usual definition of almost universal hash function. Let H be a family function from D to R. And then we say that H is a AU function if the collision probabilities between the hash result is small. We say H is AU. Next is the AXU definitions. For any element C of R, if the probability satisfying this equality is small, we say H is AXU function. For example, let H be equal to M times K. It's easy to see that there is only one key satisfying this equality. So we say that H is AXU function. Another familiar function is the Pauli. It was proved that Pauli is also AXU function. Universal hash functions have been commonly used in the design of MACs, TBCs, and AE schemes since firstly introduced by Carter and Wegman. Next, I will show you the design of the MACs. The basic idea of this kind of schemes is to use a universal hash function to compress the message and then encrypt the hash result to be the tag T. These both are the four common methods to process the hash result. Another application is the design of triple block cipher. This is the strong triple block cipher introduced in 2002. Next, I will introduce the related key attacks. It was firstly applied to block ciphers, and then a formal definitions of RK-PRP and RK-PRF were given in 2003, and they have been widely applied to mass TBCs and AE schemes and so on. So next, I will show you the related key attacks against the schemes which are based on universal hash functions. Firstly is the example attacks against MAC. This scheme is secure in the invariable key setting. But in the related key setting, we first query this message and under this modifying key, and then we get the tag st. For this equalities holds, we can predict that the tag of this message is also T under this original key. So this scheme is not related key secure in the related key setting. Next is the attack against TBC. This scheme is also secure in the invariable key setting. In the related key setting, we first query this message. Here T is the trick, and then we get the ciphertext is C under this modified key. For these equalities, then we can predict that the ciphertext of this message is CXOR T under this original key. So this TBC is not related key secure. From the above text, we can see that the key of the universal hash function is a part of key of the whole schemes. So we can make transformations to the key of the universal hash functions and found collisions between the hash result. This is the main reason that we made successful forgery. And moreover, these attacks have nothing to do with the block cipher. Unfortunately, almost all the existing two-key schemes which based on universal hash functions are not relate key secure. So we propose our new definitions of RKA-AXU function and RKA-AXU function. Here is the formal definition of RKA-AXU function. In the related key setting, the adversary can make a related key deriving transformation phi, and for this distinct phi m and phi prime and prime, then if the collision probability between the hash result is small, we say that H is RKA-AXU. Similarly, we define the RKA-AXU function like this. For any element C of R, if the probability satisfying this equality is small, we say that H is RKA-AXU function. In our paper, we take the XOR set as the default RKD set. See the poly function, we let the two message to be 0, and then this equality is always holds, so poly is not RKA-AXU function. It's a pity that almost all the existing universal hash functions are not RKA-AXU, such as MH, square hash, NH, and so on. So next, we construct the RH1, RH2, and RH3 functions. They are RKA-AXU functions. We construct two types of RKA-AXU functions. First is the fixed input length one, and another is variable input length one. First, I will introduce the RH1 constructions. We construct RH1 based on the n times k by adding the cube of k. Then we let Fk be the XOR set of the hash result. We found that there is at most two keys satisfying this quality. So RH1 is RKA-AXU function over the XOR set. It's a remark from one of the reviewers point out that RH1 may not be RKA-AXU function over the other set. For example, he defined the phi 0 set like this, and then this equality always holds over this set. So RH1 is not RKA-AXU over the set phi 0. Here we send to the reviewers for his kind comments. Next, I will introduce the variable input length functions RH2. We know that poly is an AXU function, but it cannot support variable input length. So we first introduce the padding rules. We pad minimal zeros to make the length be the multiple of the broad length, and then add the bit length of the message as the last block. So poly K pad n is variable input length functions, but it's still not RKA-AXU. So next, we add some terms like this to construct RH2. We have proved that RH2 is RKA-AXU function over the XOR set in our paper. This table gives the computation process of these two functions. We can see that RH2 only needs one more pre-computation and one more multiplication if R is even. So RH2 is almost as efficient as the poly pad n function. We may think that if this this scheme is secure in the invariable key setting. And then we think that if we replace this function with our construction RH1, and then assume the block cipher to be RKA-PRF, then the scheme whether will be relatively secure or not. So I will apply the relatively universal hash functions to design the relatively secure mask and TBCs. First is about the relatively secure mask. Here we assume that the hash function to be RKA-AXU over phi 1 and the block cipher to be RKA-BRF over phi 2, then this scheme will be relatively secure over phi 1 times phi 2. And then in Mac 2, we only need the hash function to be RKA-AU over phi 1. Then Mac 2 is RK secure over phi 1 times phi 2. Next is about the relatively secure TBCs. In TBC 1, we assume that the hash function to be RKA-AXU over phi 1 and the block cipher to be RKA-PRP over phi 2, then TBC 1 is RKA secure over phi 1 times phi 2. And in TBC 2, here pi is public random permutation, and then the hash function is RKA-AXU over phi 1, then TBC 2 is RKA secure over phi 1. Finally, let's recall what we did in our paper. We firstly proposed new definitions of relatively almost universal hash functions, RKA-AU and RKA-AXU. And then we provide several efficient constructions named RH1, RH2, and RH3. And finally, we show the relatively secure mask and TBCs composed of RKA-AXU function, RKA-AU function, and other primitives such as RK-PRF and RK-PRPs. That's all. Thank you.
Okay.